that is in B member, in any B member or in any rigid plane frame member, what is the strain energy stored, that we will derive similar to this, and these two expressions we will use it for analysis purpose. As I did here in the truss member, we will derive the strain energy due to flexural member. So the elastic curve, because due to flexion, the particular member undergoes bending deformation. It bends in the form of with compression in the top fiber and tension in the bottom fiber. So that is the actual deformation shape. That shape we call it the elastic curve. The elastic curve of a prismatic flexural member of length say L and flexural rigidity EI. There we took axial rigidity, here we take flexural rigidity EI. The elastic curve of a prismatic flexural member of length L and flexural rigidity EI will be a circular curve that you know already. Again, from strength of materials, is a circular curve when subjected to pure bending, no shear, only bending moment. If you apply, then that particular member undergoes deformation in the form like that, and that particular deformed shape will be nothing but a simple circular curve like that. It is a circular curve. The bending will be in the form of a circle. So having some origin or center O and R will be radius of curvature, L is the length and theta is the angle of curvature. So this you have derived in strength of materials. So the elastic curve will be a circular curve. A circular curve here, like this, as in figure, when subjected to pure bending, when subject to the sagging bending moment, no shear, only when it is subject to pure bending M, right? Instead of axial force, pure bending, it results in the form of a circular curve. Then from geometry, you know, L is equal to R theta, bending as in figure. We have from geometry, theta, R is equal to L theta, or theta is equal to R by L by R. L is equal to R theta. So L is equal to R theta, or theta is equal to L by R. So this we call it as B. Here I took the deformation delta as FL by A. Here the deformation is rotation on account of pure bending, that is given by L by R. But from flexural formula which you have derived, in strength of materials, you have that famous bending equation M by I is equal to E by R is equal to sigma by 1. From this, so therefore 1 by R is equal to M by EI. 1 by R is equal to M by EI. Therefore, from B, theta is equal to ml by EI. So there I got delta is equal to PL by AE in the earlier expression. Here it is ml by AE on the same argument as I did there. So L, EI are constants. Therefore, theta is some constant into m. That is, theta is proportional to m. So if you plot a curve of m versus theta, there we plot the curve of P versus delta. Here I can plot a curve of m versus theta. Then again, since L and EI are constant, it has to be a straight line, linear variation. It has the value of m here and corresponding value if I take here theta. Then again, the total work done, external work done on account of this bending will be the area under this particular curve, and that will be stored inside as strain energy. Therefore, that strain energy is equal to that area half into, instead of F delta, you will get m theta. So you will get an expression for strain energy due to bending. So this is as simple as that. Similar to that, strain energy is stored due to flexure. One, you have to remember this. Whenever it is subject to pure bending, that elastic curve will be a circular curve, like this, having some radius of center L. L is the origin, then M is the moment. So you have from geometry that relationship, and from flexible formula that relationship, you can get the expression for strain energy. So this expression, you call it as, this I don't call it as B, I will call this as B. Theta is equal to ml by AE. So in B, we see that since L, EI are constants, there exists a linear relationship between m and theta. There exists a linear relationship between m and theta as in figure. That is this figure. There exists a linear relationship between m and theta. You just go on taking different values of m, measure it theta, plot it, you will get a straight line. So hence the total external work done, thus the total external work done will be is equal to area under curve and is stored as internal strain energy. That is defined as strain energy. It is nothing but external work done, right? And that external work done will result in internal strain, and that energy will be stored inside that. So thus, strain energy is equal to half into m theta here. So substitute value for theta. So or u is equal to half into m into ml by EI, or it is equal to m squared L by 2 EI. Right? So this expression for strain energy is in terms of force applied only. Force applied is pure moment. Yeah. Force applied is moment here. It is that. So, therefore, in terms of, this is another form. If you substitute in terms of theta, if you substitute, or before substituting, I will just explain with respect to a beam, as I explained with respect to thrust in the other case. So this is the expression for strain energy. Now you consider a beam member AB, any member of a continuous beam or any member of a rigid plane frame. They are also beam only, subjected to bending. If you take any member like this, so if you take a segment here, dx, and this beam is subjected to some kind of loading, and L is the length of the member, and the bending moment diagram is somewhat like that, and in this segment dx, if mx is the bending moment, then the expression for strain energy stored in that segment or element will be mx square. Instead of L, you have dx divided by 2ei, and here is the flexural rigidity. Now, next, now consider a beam of length L and flexural rigidity ei, subjected to vertical load as in figure, like this, subject to vertical load as in figure. So consider an element of length dx at a distance x from it, at distance x from left hand. Let mx be the bending moment, at this element or for this element. Then strain energy stored in the entire beam, you can take it as the integration of the strain energy due to the element. Element is given by this expression. Therefore, strain energy, the beam U is equal to, in the element, it is mx square, length is dx divided by 2ei from this. That is your strain energy in the element. In the beam, so like that I can have number of elements taking from x is equal to 0 to x is equal to L, 0 to L. Or in other words, integrals mx square dx by ei. This is the expression for strain energy due to
bending.
In beam due to bending only, or due to force only. So due to displacement. So similar to that, you can write it. So this you call it as 2. So if you have number of elements, suppose if you have frame, here you have 3 elements. Suppose you have a continuous beam, wherein you have number of beam elements. So in one element, it is like that. So like that, if you have number of elements, you have to add it. So then you have to use a sigma notation. I is equal to 1 to n. Similar to thrust. For each element, you can determine from that by integrating that, and for all you can add for all that element by finding strain energy stored in each element. Is the principle clear?
Yes.
This is the main thing you have to remember. In axially loaded member, it is P square or by F square L divided by 2AE. Here it is mx square dx by 2A integral. And again for all total structure, it is summation. So, equation 2 is the expression for strain energy in flexural element in terms of force only, right? So in terms of displacement, on same, right? Or you can say mx is equal to E d2y by dx square. That also you know already from spectral material. Using that, you can write that u is equal to 1 over 2vi d2y by dx square whole square dx. This is in terms of displacement. Displacement is the curvature. d2y by second derivative of deflection y is curvature or theta square. This is nothing but theta square. So this expression. Okay. So expression for strain energy due to bending due to axial force, and expression for truss structure strain energy, expression for frame or beam member due to strain energy. That you can remember. I will write it as right hand corner, the expression for the analysis which you have to remember. So for trusses which are basically axially loaded members, the expression for strain energy is given by Fi square Li divided by 2AE I. You can remember this. And for beams and frames, rigid frames. So the expression for strain energy, this is rigid plane frames. U is given by sigma of mx square dx divided by 2di. So these are the expressions which I have derived. Now, these expressions you can use for analysis of beams, trusses, and rigid plane frame. Basically, evaluating the deformation, slope, and deflection. You can use this by applying Castigliano's theorem. So this is the theory which you have to remember. Next, I will take up the Castigliano's theorem. That also I will state it. Two theorems are there, so that you will use it straight away